Okay, hi guys. So today we are doing the Doppler effect. Okay, so by the end of this lesson, you should be able to define and explain the Doppler effect, and you will be able to calculate variables based on your Doppler effect. So first, you need to know the definition of Doppler effect. And I am gonna give you a hint here and tell you to memorize this because every past paper I have seen, they have asked you to define this. It is two marks done and dusted. So the Doppler effect states that it is the change in the observed frequency of a wave when the source of the detector moves relative to the transmitting medium. Okay, so what it's basically telling you is you as the observer will hear a different frequency to what the source might give off based on where you as the observer is away from the source or the source is away from you. Okay, and we can apply this to sound and to light. So I'm first gonna just explain that using my whiteboard. Okay, so in front of you, there are these little circles. And what I was trying to show you is this is your source. Let's say this red dot over here. And the source is standing still. So not moving. And visualize your sound waves as if they make ripples. So if you think about taking a rock and throwing it into water, and it makes these ripples on the water where you see your waves going out. That is how you have to visualize sound waves now. So if you look at this, you've got your source and it's making a sound. So you've got your first wave over here, then the second wave, then the third wave, and then the fourth wave, okay? And so the distance between these waves are identical. So this distance doesn't change. And we can say it is the V of wave. Okay. On this side, I have now taken the same picture, but I have said that my source is moving. And so what is happening in this picture is your source is moving to the right. Okay, so what you then see is that as the source is moving to the right, your distance between your waves is actually exactly the same as it is when it's stationary. But what happens is as the source starts moving to the right, these waves at the front, okay, they're gonna bunch up. So let's say they bunch up. And these waves, let's just look a different color. Okay. These waves here at the back, they're gonna be further apart. Okay, and so one really important thing to remember, in grade 10, you started off with waves and we learned that sound waves are compression waves. So what that means is, let me just draw here. The sound wave is a compression wave, or the other thing is we call it a pressure wave. So you've got your thick areas where you've got a lot of particles, and I'm coloring them in the solid green. And then you've got your thinner areas. No, Carlos, we are doing the Doppler effect, but I'm just recapping on what a sound wave is. Then you've got your thinner area that still has particles, but they're not as closely pressed together. And then you've got your closely pressed together. So these areas here, your particles are very close together. And that is what is indicated by the solid black circles that I drew. These areas here, you still have particles, but they're further apart. So further apart, sorry. So what happens is, over here with your yellow, when they're bunching up, we're basically saying that those intense lines are getting much closer to each other. And you only have a small bit of this open space in between them. Whereas here, where they're further apart, we are saying that you've got your big particles coming close together, bunched up, and then you've got a much bigger space. Okay, and why that is important is with the Doppler effect, we are trying to explain why someone standing on the sideline hears the frequency differently to what is being given off by the source. So if I quickly erase that bit. Imagine that there is a guy standing over here, and there is a guy standing, whoops, over here. Okay, so let's say this is person 1, and this is person 2. And we say the same for they're standing at the non-moving source. Person 1 and person 2. Okay. So if we look at the non-moving source first, who do you think is going to hear the sound the most or the loudest, or is there going to be a change in what they're hearing? Is person 1 going to hear it differently than person 2? If we're just looking at this non-moving source, what's going to happen with person 2? What do you think? Do you think there's going to be a difference in what the two people hear? Let's say this person is 5 meters apart away, and that person is also 5 meters away. Okay, yes, so everyone is correct. Over here, there's going to be no difference in what they hear. Oops. Okay, if we now go to the moving source, and that person is 5 meters away from the most outer wave, and this person is still 5 meters away. But remember, the source is coming closer. Who's going to hear the sound the best? Person 1 or person 2? Yes, Mosaico, person 1. And person 2 is going to start hearing it the least. So for person 1, this person is going to hear an increased pitch. An increase in pitch. Because as this source is moving towards her, these waves are bunching up. They're coming closer together. So she hears it a lot louder than this person at the back who hears a lower pitch. Because his sounds are further apart. Okay. One thing that's really important though is that your V wave, the sound of your wave, the speed of your wave does not change. Okay. The only reason that this image looks different is because of the fact that your source is moving. Yes, Bob, the pitch increase is caused by the fact that your waves are now closer together. So you hear a louder sound. That person's going to hear an increased frequency. Whereas this person behind, who is further apart from the source and the particles are spaced out further, will hear a lower pitch. Okay, but the very important thing is the spacing between your waves is still the same. It's distance. That does not change. The only thing that is changing is the frequency. So there's a change in frequency. Okay. The wavelength stays the same. That's not changing. We're just looking at the frequency that is changing. Okay, so that's very important to remember. Okay, so just gonna go back to my slides. Okay, so as I was showing you now, 4 things can happen. So first of all, your source can move, and your source can move towards an observer or away from an observer, or the observer can move. So the observer can go towards the source, or they can move away from the source. They were both 5 meters away from the wave, the most outer wave, but they weren't 5 meters away from the source. So their position relative to the source has changed, not to the most outer wave. That's why the pitch changes. Okay, so if you look at this picture, and this is kind of what I was trying to draw, not that great at it. This police car has its sirens on, and it is moving towards this person at the front. So there's going to be a high frequency. You're going to hear this frequency change. Okay, this person is going to hear an increase in pitch because these waves are being bunched up closer together. Whereas this person at the back is going to have a lower frequency or a lower pitch, and they're not going to hear the wavelengths that much. No, I'm sorry, I meant the speed of the wave. Sorry, the V, not the lambda, the V. Your V is going to stay the same. The speed of your wave remains the same. The speed at which the frequency is the source is emitting the wave. So if your frequency changes, obviously your wavelength changes, but the speed remains the same. So the V wave stays the same. So your waves are being bunched up, then you see here they're getting closer together. So your frequency is increasing, shorter wavelength. As your wavelength increases, your frequency decreases. Then, okay, so this is for your moving source. So as in the pictures, one person standing in front of the source, as the source is moving towards them, they will hear an increased pitch. And then your other person at the back will hear a decreased pitch. And then on the other side, we can have it that you have your observer that's moving. So in this picture, you've got a guy and he's listening to a stereo. And he is walking away from the police officer, and the police officer is walking towards him. So as he is walking to the right, he is moving and bunching up his waves at the front, in front of him. And they are being more spaced out behind them. So you can see the wavelength changes. And the frequency will be increased here at the front, decreased here at the back. But like I was saying, your V of your source, your speed of your wave is going to remain the same. That's why your that is normally what we tell you. Yes, it's the speed of sound, but they can make it whatever they want to in a question. They don't necessarily have to keep it 340, but we do. That's just normally the speed of sound in air. But obviously, if it's in water or something like that, Chad, it could change depending on your medium. Okay. And so as this police officer is walking towards him, he is going to walk into these different wavelengths, and he's going to walk by bunching them kind of closer together. So he's going to start hearing an increase in sound because he's walking closer together. And as he walks to the right towards the waves, they kind of bunch up for him. Does that make sense? So the big thing here to understand is that there's a difference between your moving source. So over here, your source moves and the waves kind of move with him because that's where the source is coming from the police car or the fire truck. Okay, and the fire truck or police car is moving and the waves are moving with him. But over here, you've got this policeman and he's walking towards the wave. Then there's also a bunching up, but you can't draw it in the same way that you can draw your moving source. Not that they'll ask you to draw it, but you kind of have to visualize these questions to be able to explain them. Okay, so this brings us to the most important part, the formula. So your formula will always be FL is equal to V plus or minus VL divided by V plus or minus VS times times Fs, okay? So if L stands for the frequency of the listener, so what the listener will hear. If S is the frequency of the source, so what the source is giving off, okay? VL is the speed of the listener. So that is what, if you're the observer, that's what you will hear. The speed of you if you're moving. So are you standing still? Are you moving? That's basically what they're telling you. VS is the speed of the source. So what's happening to the police car, for instance? Is the police car standing still? Is it moving? What's the speed that it's moving with? Is it moving towards or is it moving away? And then V is the speed of the wave. And like Chad was saying, it is normally going to be 340 meters per second, unless they state otherwise or you are in a different medium. Okay. Then the plus or minus comes from the fact that are you moving away or are you moving towards the object or the source? Okay. So if you are going to add your VL, then it means that the person is moving towards the source. So if this becomes a plus, if you're adding, then it means that the person is moving towards the source. If you subtract the speed of the listener, it means that that person is running away from the source. Okay. At the bottom, if you add your VS, the speed of the source, it means that the person is running away, the source is moving away from the observer. And if you subtract the speed of the source, it means that the source is moving towards the observer. I haven't really ever seen a lot of questions where they ask you a scenario where both is happening at the same time. It's normally one or the other. So a way to think about it is, think about it in terms of your denominator and your numerator. So let me just get my whiteboard. Okay. Okay, so let's say you have this scenario. So like I was saying, I'm going to look at when they're only asking you one way. Okay. If you have this scenario where you are subtracting your speed of your listener, it means that you are running away. And how do we know that? In this case, your numerator is going to be less than your denominator. So it means you're going to have a value less than 1. Okay, in your brackets, inside of your brackets. If, however, your person is moving, your observer is moving towards the sound, like over here, then your denominator is going to be smaller than your numerator. And your bracket value is going to be greater than 1. Okay. If we're looking at your source, when it is this way, when you are subtracting the speed of your source, then it means that your numerator is greater than your denominator. And that means that your brackets will have a positive value, greater than 1. If you add that value to it, it means that your denominator is going to be greater than your numerator. And your brackets will give you an amount less than 1. So if you then multiply that, you'll get a smaller value. So if you're not sure what's happening, always think about what happens with your numerators and denominators. That's the easiest way to argue out what to do. Okay, so like I was saying, we normally refer to sound, what you're hearing in terms of pitch. So when the sound is moving towards something, your waves will be bunching up, so you will have a high frequency. And when you have a high frequency, that means you will hear a high pitch. So you will hear a loud sound. When your sound moves away from something, your waves are spreading out. So they're moving further apart, your particles are further apart, and your frequency is low. So you will hear a low pitch. Okay, so we are quickly going to do an example. So they tell us that the siren of an ambulance emits sounds of a frequency of 700 Hertz. You are standing on the pavement. If the ambulance drives past you at a speed of 20 meters per second, what frequency will you hear? And then the first one is as the ambulance approaches you. So oh, sorry, Luke, I'll quickly go back, my bad. That one? Okay, cool. Okay, so as they were saying, you have an ambulance and they're telling us, let me just write what they told us. So they told us that the ambulance was emitting 700 Hertz. And they told us the ambulance was moving at 20 meters per second. We know that the speed of sound is equal to 340 meters per second when it's in air. And they were telling us that you or the person waiting for the ambulance was standing still. So your VL in this case is going to be -1. So the first one, they were asking us for when the ambulance approaches you. Okay, so first things first, always write your formula because you get a mark for the formula. Okay, so our V in this case is 340, so you substitute that in there. And our VL is going to be 0, so I'm not going to bother writing it in there. If you do, that's cool. Probably a good practice to have. So let me just write it in there. 340. Then we are subtracting it because we know that the ambulance is moving towards us. So it's important that you subtract this amount over here. And we multiply it by the 700 Hertz. Okay, and if you plot that into your calculator, you should get, I get 743.75 Hertz. Is that what everyone else gets? Yes. Thank you, Eli. Okay, so that was the first one. Then the second part of the question, they asked us when the ambulance moves away from you. Whoops. Okay, so once again, write your formula. And then we can substitute in our values. So 340 plus 0 divided by 340. And now the ambulance is moving away. So we have to add the 20. And we multiply it by 700. And now our answer should be less than 700. So if we put it into a calculator, we get, yep, 661.11 hertz. Oops. Okay. So most important here is being able to decide whether you're going to add or subtract. So if we go back to the PowerPoint. The top doesn't matter. Because of the fact that you're standing still, you could have actually just left out the 0. I just put it in there because it's kind of good practice. But if you didn't, if you just left it as 340 over whatever, that would have been acceptable as well. So whether you add or subtract, it's 0, so it's not going to change your top number. Okay, then the next example, they tell you, what is the frequency heard by a person driving at 15 meters per second towards a factory whistle that is blowing at a frequency of 800 hertz? Assume that the speed of the sound in air is 340 meters per second. Chad, if there was a number in instead of 0, then you would have to decide for yourself, is the person moving away from the source or towards the source? So that would be a scenario where they're telling you, I don't know, someone's driving towards you and you're running towards that car, some GTA thing. But normally I haven't really seen questions where they ask you guys that at school level to do both. Okay, so what they told us was speed of sound in light was the 340 meters per second. And they told us that you were moving at 15 meters per second. They said that the source was a factory, so obviously it's standing in one place, was standing still. They told us that the factory was emitting this whistling sound at 800 hertz. And they were asking us, what is the frequency that we hear? Okay, so step 1, write your formula. Oops, the L, my bad. Okay, so the L is equal to brackets V plus or minus, whether V plus or minus Vs times Fs. Okay. In this case, we know that we are running towards the building or the factory. Yes, Fs stands for the frequency at which the sound is being emitted, the frequency of the source. So that's if they give you that frequency, they can change it up and ask you for the frequency at which it was emitted. Okay, so this is going to be 340 plus 15. Okay, because we know we're running towards it. Divided by 340. And I'm just going to say plus 0 again. But like I was saying, you don't have to. And then we multiply it by 800. And that gives us, thank you, 835.29 hertz. Okay, so here you basically had to notice that you are running towards the source, and that means that you add the top number and that your number. So a way to double check yourself is always think about it logically. So if you're moving towards something, you should get a higher frequency than what the frequency was being emitted at. So if this amount wasn't greater than 800, you would have known that you made a mistake somewhere. Okay. Then, example number 3, they tell us that Cecil approaches a source emitting sound wave with a frequency of 437.1 hertz. First question asks, how fast does Cecil need to move to observe a frequency that is 20% higher? The second question asks, if he passes the source at this speed, what frequency will he measure when he is moving away? And then once again, we need to assume that the speed of sound in air is 340. No. This first one, they are actually asking us to calculate how fast you're moving. So no, it won't always be frequency. They can ask you any one of those variables, Barney. It is their prerogative. Okay, so let me just make space here. Okay, so first, just gonna write down, they told us that our Fs was equal to 437.1 hertz. Okay, then they told us that your FL is 20% higher than the Fs. So what that means is you need to now put this in decimals. And so FL in this case is going to be 1.2. And we're leaving it as that because we are now going to work with ratios. So first we have to write our formula. Times by VS. Okay. Then what I'm going to do is I'm going to divide both sides by VS so that I get a ratio on this side. Okay, so now we have VL over VS is equal to V plus or minus VL divided by V plus or minus VS. Okay. And I'm going to substitute this in here. So 1.2. And then, by the way, we know that it's stationary, so that bit can fall away. So they're telling you that your VL is 20% higher than your VS, Sukanye. So that means if you think about it in terms of decimals, 20% is 0.2. So you just add 0.2 to 1, 1 being 100%. So you now have 120% of what you originally had. Does that make sense? Okay. Then if I add in this 1.2, that means that it is 1.2 of Fs. So there's a reason I added it in. So that means that my Fs can cancel out now. So now you just say 1.2 is equal to V plus or minus, and in this case, it should be plus because they were telling us we hear a higher frequency, so that means the source is moving towards, oops, the listener is moving towards the source, okay. And then I'm just going to change that bracket that it becomes 1 plus VL over V. And the reason I can make it that is because we are basically saying V over V plus VL over V, which is equal to 1 plus VL over V. Okay, then I can subtract 1 from both sides, and you have 0.2 is equal to VL over V. Yeah, I'm just going to take it up to the top here. So and then we know that V is always equal to 340, or they even said it in the question. So we can substitute that in there. So it's going to be 0.2 is equal to VL over 340 times both sides by 340. And we should get our answer for VL. So VL is equal to, I get 68. Has anyone done their calculation? Am I right? Yes. Okay, cool. So yeah, this one was a bit of a tricky one. The English might get you if you're not an English speaker, native English speaker, like that's not your first home language. So what you were supposed to see is the 20% higher means that this over here is 1.2. So 20%. So if it was less, okay, so this is important. Let's say they said it was less, then your FL would change to 0.8. Okay, so you always have to think in terms of percentage being 1 and the decimal that your percentage would be. So 20% is 0.2, and then whether it's more or less than what it originally was. So if they told us it was less, then it would have been 0.8 FS. And then you would have done the exact same thing, but this value would have changed. Okay. So then the next half of the question said, let's just go back and see. They asked us if he passes the source at this speed, what will the frequency be when he is moving away? Okay, so in the second question, they're asking us to calculate FL now. So I'm going to do it on here in the corner. So they're asking us, what is FL if we now use these values that we have found? So first things first, always write your formula. Oops, I'm supposed to write my formula, my bad. Okay, so 340 minus 68, because you're not moving away from the source. So it's minus. And we are multiplying it by Fs. And Fs over here was 437.4, so we could put that in there. 4371.1. And you should get, I get 349.7. Did everyone else get that? So as you are running away from the building with the same speed that you were running towards the building, you will now hear the frequency as 349.7. Hertz. Okay, so does it make sense how you need to decide whether it's going to increase or decrease, and how you look at it? So the biggest thing is seeing whether your person is running away or towards the source, or whether the source is moving away or towards you. And like I say, if you can't remember, always think about your denominator and your numerator and the relationship between the two. Okay, then the fun side of the Doppler effect is that we can actually apply it to light. So hopefully from grade 10, you remember the electromagnetic radiation and that table that we used to show visible lights and the colors and the wavelengths that they had. And so if you look at my beautiful little picture down there, you will see that your blue colors or your violet color had a high frequency and a very short wavelength, and that your red colors, oranges, were lower energy, so they had low frequency and very long wavelengths. And so the beauty of this is that we can actually say whether something is moving towards or away from Earth, and what we call it is a redshift and a blueshift. So if you look at this picture over here, you've got a little light bulb in there, and it shows that the light bulb is moving to the right, towards this human being on the right, and that's what we call a blueshift. And so what happens is if you look at this light source using a telescope or a specific technology, the heat being emitted off of that source will be the color blue, because the wavelengths are, the frequencies increasing. So that can show us that it's coming towards us. Whereas if you're the person on the left-hand side from which the object is moving away from, you will have longer wavelengths, which means you will have a lower frequency and you will see the color red most likely. And that is called a redshift. And this type of technology has actually enabled people at NASA, or there's a place in Korea that actually also does it, to prove that the universe is expanding. And a lot of people are using that theory that the Big Bang is how we actually came to be. Because if you look at space and you look at all the stars, they project this red light. No, they project, yes. They project a red light, which means they're moving away from us. And so it's showing that the universe has to be expanding in order for this red light to be seen instead of it being blue. Whereas obviously, if you had to look at something like a meteor that was coming towards Earth, we would see a blue shift. So this is just a little bit of theory that they put in. Most of the question papers, it would be a 2 or 3 question mark paper question where they would just ask something like, how can we prove that the galaxy is expanding, or explain what it means that the stars are giving off red lights or something. Then they're basically just asking you to explain what a redshift is and what a blueshift is. Well, I don't know, Salma. That means hopefully we find better places out there with people who care for each other. No, it actually doesn't mean anything for us. We can't do anything about it. So if the Earth is expanding, well, the Earth isn't expanding, the galaxy is expanding. It just means that things are moving further apart and more things are coming. We honestly, to be quite honest, I don't think we understand the impact of it yet, or what it really means. It's quite an interesting science to go and look at, astrophysics. But it just, for us, it just shows that the Big Bang Theory might be a thing. Okay, so we are almost out of time. Like I was explaining, just be able to do the redshift and blueshift. I will show you how to answer that in a question paper tomorrow. Tomorrow we will be doing past papers, working through 4 different past papers, and hopefully by the end of it, you will be good with the theory. So tomorrow we're just doing past papers. We'll answer all the questions and see where this takes us. I hope Doppler effect making more sense now. See you guys tomorrow, same time, same place.